When I first heard about this, I thought it was going to be huge news. I mean, gravitational waves rippling through space from the very beginning of time itself, a literal shaking of the foundations of reality. And yet, despite headlines around the world, the scientific community at large has been strangely silent. Why? Have we discovered the smoking gun for our most popular theory of the early universe, or is it just another dud? Let's have a look. This news is about primordial gravitational waves. But what are those? Gravitational waves are ripples in space-time that can be generated whenever massive objects accelerate. For example, when a neutron star or black hole forms in the early universe, that can create a gravitational wave. These waves then travel outwards at the speed of light. They stretch and squeeze space as they go, which makes it sometimes easier and sometimes harder for light to get through. If you want to learn more about gravitational waves, check out my science show video on the occasion of the first detection of gravitational waves in 2016. But for primordial gravitational waves, the situation is somewhat different. Those would be the gravitational waves that were created in the earliest fractions of a second after the Big Bang. The reason why this is interesting is that the most popular theory of how the universe began, so-called cosmic inflation, predicts that these primordial gravitational waves exist. This idea of inflation says that the universe did not start off with a Big Bang, but rather with a quantum fluctuation that rapidly expanded, creating the seeds of all the large-scale structures we see today. This quantum fluctuation is supposed to have generated a lot of energy that today manifests itself as gravitational waves. The thing is now that these waves should have a specific and unique polarization. Polarization is a property of waves that describes the direction of oscillation relative to the direction of travel. You can think of it like this. Imagine you have a rope attached to a wall and you move one end up and down. A wave will travel along the rope. If you move the rope up and down in one plane, that's a linearly polarized wave. But if you move it in a circular fashion, that'll create a circularly polarized wave. Light waves, for example, can also be polarized, and the polarization of light is what makes sunglasses with a polarizer actually useful because they only let certain polarizations through. For the gravitational waves from inflation, we expect a specific polarization pattern that would be a direct and unambiguous signal of the inflationary epoch. The only problem is that the signal would be extremely weak by the time it reaches us. This is because gravitational waves lose strength as they travel. This means we wouldn't be able to measure the gravitational waves directly, but we might be able to see the effect they have on light that travels through them. So basically, we're looking for a very specific pattern of tiny variations in the polarization of the cosmic microwave background. That's what Nanograv and the other groups are looking for. Nanograv is a collaboration of more than 200 scientists from around the world working on this experiment. They pool their data from various radio telescopes around the globe to create a map of the polarization of the cosmic microwave background. Primordial gravitational waves would confirm the idea of cosmic inflation, which is currently the best explanation we have for how the universe began. They'd also tell us something about the mechanism that drives this inflation. But that's not all. These primordial gravitational waves are also a prediction of some theories of quantum gravity. Yes, that quantum gravity that keeps evading physicists at every turn. There are many different theories for how gravity should work when we're talking about very small distances and very high energies, but none of them have been confirmed so far. The thing is now that each of these theories of quantum gravity makes different predictions for the polarization of the gravitational waves. So finding the primordial gravitational waves and measuring their polarization would also tell us which, if any, of these theories of quantum gravity is correct. And this is where things get difficult because while the data analysis is finished, the results aren't out yet. It's not that they haven't found anything. No, they actually report an excess of gravitational waves in the data. The signal they've detected doesn't fit to the expected stochastic gravitational wave background. But unfortunately, they say the excess could also easily be due to instrumental errors, or in other words, noise in the data. In their paper, they write that given the current data set, it is impossible to draw a definitive conclusion about the presence or absence of a stochastic gravitational wave background. In the press release, the spokesperson for Nanograv, Denny Cole, says that this result keeps them up at night. Personally, I find it very exciting even though the result is somewhat ambiguous. This is because there have been several other experiments that have found similar anomalies. For example, the Bicep collaboration said last year that they also have data that can be interpreted as a signal of inflation. And even though that signal has turned out to be most likely due to dust, the issue isn't settled. There are still a few analyses pending, including one from the Planck collaboration. So stay tuned. If you think this topic is as exciting as I do, you should really subscribe to my channel. I promise to keep you up to date. Thanks for watching. See you tomorrow.